Hello and welcome. Today I'm going to be looking at an AQA Higher GCSE paper. This is the November 2018 non-calculator paper 1, unit code 8300/1H. Question 1. Simplify 5 to the power 4, subsequently to the power of 2. So this is a simple application of one of the basic index rules. Whenever you have a power on a power, you take the product of those powers. So 5 to the 4 and then to the 2. What do? You do 4 times 2, and that leaves you with a subsequent power of 8. So just to remind us to why this is, if you had something like 2 cubed, and then you were to say, take that to the power of 4, well, 2 cubed is 2 times 2 times 2, because you're just timesing 2 by itself 3 times, and then you're taking that to the power of 4, which takes a lot of writing, but I'll do it once just to show you. So 2 times 2 times 2 times 2, and then you're timesing that by itself 4 times, so it takes 4 rows here of 3 2's. And how many products does that leave us with? Well, you get 2 times by itself 12 times over, right? That 12 is 4 by 3. That leaves us with 2 to the power of 12. This 12 is the product of the 3 and the 4, and that's why that rule holds. Question 2. Circle the volume in centimeters cubed of a cylinder with radius 5 centimeters and a height of 8 centimeters. So a cylinder is essentially a circular prism. What is a prism? It's a 3D shape where the cross-sectional area is uniform throughout. So the cross-sectional area for a cylinder is just a circle. How do you find the volume of a prism? Well, you take the cross-sectional area and you times it by the height or the depth of that prism. So for a cylinder, the cross-sectional area is just a circle. And the area of a circle is pi times the radius squared. So if we take pi times the radius squared and then times it with the height, what we're going to achieve is the volume of a cylinder. Now in our case, the radius is 5, so pi times 5 squared, and then times by the height, which is 8, and that will give us our volume. 5 squared, 25, times by 8, times by pi. What is 25 times 8? That is 200. So we get 200 times by pi, which we can otherwise just write as 200 pi. And that's our volume. And the unit for that would be the centimeters cubed, because what we've done there, this 5 here was centimeters, and we've squared that, so that could be centimeters squared, and then we're timesing that by the 8, which is also centimeters. Centimeters squared times centimeters will give us centimeters cubed as the final unit. Question 3. Simplify 16a squared, subsequently divided by a, in addition with 3a times by 2. So for this question, you absolutely need to know what operations to evaluate first over and above other ones, right? So here we have the operations of divide, we have the operations of addition, and we have the operations of times. Now by convention, you evaluate division and multiplication before you try and do any addition. So that means, well, we want to do the 16a squared and then divided by a first. And that essentially constitutes this first term on the whole. Another way of writing that would be 16a squared and then all over a. And one of the a's here is going to cancel with one of the a squareds, right? Because a squared is just, well, what is it? It's a times by a. And now we have a factor of a in the top and the bottom. So one of these a's is going to cancel, and you're just going to be left with 16a. And that's what the first term simplifies to. What about the second term here, this 3a times by 2? Well, 3a times by 2, that's like 3 times a and then times by 2. And because it's all being times together, it doesn't actually matter what order you times it in. So you could quite easily think of that as just 3 times 2 times a. And then you can do the 3 times 2 first, if you like, which is just 6. And then 6 times a just leaves us with 6a. And now we're taking the addition of the 2 terms, 16a, in addition with 6a. And that's going to leave us, well, 16 lots of a plus 6 lots of a. That only leaves us with 22 lots of a. So the answer here is 22a. Question 4. Circle the value of cosine of 30. So to answer this question, you want to be familiar with your common angle triangles, otherwise known as special angle triangles. These are the triangles which involve the angles of 30, 45, and 60 degrees. So let me first show you the one with 45 degrees in, just to show you how this works, right? So you start off by drawing a triangle. And I'm going to say this angle here is 45 degrees. And I'm going to say this angle here is a right angle. So that necessarily means this other angle would be 45 because the angle inside a triangle is 180, right? This one here is 90, 45, 45. It's going to be 90 together, so 90 plus 90 gives you the 180. Now that necessarily means that this triangle is isosceles. So we have a line of symmetry, and therefore this length here is equal to this length here. And we're free to call whatever, we can call these side lengths anything we want. All that really matters is the ratio between the side lengths. So just to keep things simple, I'm going to call this a side length of 1, and I'm going to call this a side length of 1. So we can now find the hypotenuse length using our good old friend Pythagoras, right? So Pythagoras says this side squared plus this side squared is equal to this side squared. So what does that leave us? 1 squared plus 1 squared is equal to the hypotenuse squared. Let's call it h squared. 1 squared is 1 plus 1. That leaves us with 2. So the hypotenuse squared is equal to 2. And therefore the hypotenuse itself is the square root of 2. So that gets us started. Okay, so now we can think about what sine, cosine, and tan of 45 degrees is. Right? Let's put 45 in there. So sine of the angle, by definition, is the opposite to that angle divided by the the hypotenuse of the triangle. So the 45 degrees here, let's look at that one. The opposite to that angle is this side length here of 1. That's the opposite to the 45 degrees in the lower left. So the opposite here is 1. And then you want to divide that by the hypotenuse, which is root 2. Hypotenuse is always opposite the right angle. So you can see how sine of 45 is just 1 over root 2. And you can do the same thing here for the cosine as well as the tan. So if you did say cosine of 45, well, the only thing that changes here is you want to do the adjacent divided by the hypotenuse. So the adjacent to the 45 degrees here, well, what is that? Here's my 45 degrees. Here's my adjacent right here, and you can see it's just the same. In this case, it's just 1. So the adjacent divided by the hypotenuse, which is root 2, is going to be my cosine of 45. What about tan? Tan 45. Well, tan by definition is equal to the opposite divided by the adjacent, right? So the opposite here is 1. This guy, 1. The adjacent here is 1. And 1 divided by 1 is just 1. So this tells us what sine, cosine, and tan of 45 degrees is, right? 1 over root 2, 1 over root 2, and then 1. Quite a common thing to do here is to rationalize the denominator on the top and the bottom. So at the moment we have a root 2 in the denominator. That's an irrational number, and you can easily rationalize the denominator here by timesing the top and the bottom by root 2. And what's that going to leave us with? It's going to leave us with root 2 all over 2. And that's quite a common thing to do when you're dealing with these fractions. So that's the first, what you might call special angle triangle. There is another one, a little bit different in its construction. So here's the basic idea. You start off by drawing an equilateral triangle, if I could draw triangles, and because it's equilateral, the angles are going to be 60 here and then 60 here, and I'll just leave this one open for a second. And again, we can call the side lengths whatever we want. It actually makes a lot of sense to call the side lengths 2 here, because what I want to do is chop this down the middle And I'm going to chop this bottom side length in half to give me 1 and 1. So that would do us with a right angle here. And then finally this angle here would be the remaining 30 degrees. Because I'm chopping the 60 degrees at top there in 2 equal pieces. Okay. So we now need to find the height of this equilateral triangle. Let's call it the H right there. How do we do that? Well, yet again, Pythagoras, right? So Pythagoras says the 1 squared here plus the H squared is going to be equal to the 2 squared. And that's going to tell us what the height of this triangle is. 1 squared is 1, H squared is, well, H squared, and then 2 squared is 4. We can rearrange this. You minus the 1 over here. It's going to give us the H squared equals the 3. And then finally, you want to square root both sides. The H is going to equal square root of 3. So the height is square root of 3. Now we want to focus on this right angle triangle here. This guy right here. This is all we're interested in. The height is root 3. Sorry, I'm making a bit of a mess of that. The height is root 3, and the angles are 30 and 60, and the other side lengths are 2 and 1. So what does that tell us? It tells us what the cosine, as well as sine, as well as tan of the angles 30 and 60 degrees are. So let's have a go at that. Let's start with sine of 60. Sine of 60. Well, by definition, sine of the angle is the opposite divided by the hypotenuse. What is the opposite to the 60 degrees here? Well, it's just my height, which is root 3. So root 3 is the opposite. And then you want to divide that by, well, the hypotenuse, right? Opposite of hypotenuse. So the hypotenuse here is 2. So sine of 60 is just root 3 over 2. You can do the same with cosine. Cosine of 60. What is that going to be? Well, you look at the 60. The adjacent to the 60 degrees is 1. So you put the 1 there and then divide by the hypotenuse, right? Adjacent over hypotenuse. What's the hypotenuse here? It's just the 2. So you can put the 2 there and you can see the cosine of 60 is just a half. All right. What about the tan? Tan of 60. Quite a few to do here, right? So tan of 60, what is that? That's the opposite over the adjacent. Here the opposite is the root 3 and the adjacent is the 1. So tan of 60, you can see it's just root 3 over 1, which is just root 3. Okay, and obviously we can do the 30 degrees here as well. Very similar kind of thing, except the opposite and adjacent flip around. Let me show you what I mean by that. So sine of 30, what is sine? It's the opposite over the hypotenuse. But this time we're looking at the angle 30, and the opposite to the angle 30 is now this side length of 1. Because it's the side length is opposite in relation to the angle itself. So you put a 1 on top, that's the opposite to the 30 degrees, and then you divide by the hypotenuse, which is 2, and you can see how sine of 30 is just 2 itself. Sorry, a half. Cosine. What about cosine? You put in 30 degrees for the cosine. So what is cosine? It's the adjacent divided by the hypotenuse. We're looking at the 30 degrees again. The adjacent to the 30 degrees is the root 3. So you want to do the root 3 and then divided by the hypotenuse, which is 2. And that's it, right? And then finally tan of 30. What is that? Tan of 30 degrees. Again, 30 degrees here. We're doing opposite divided by the adjacent now because it's tan. The opposite is 1. The adjacent is root 3. So it's just going to be 1 over root 3. And again, this is one you could rationalize the denominator on. If you really wanted, you can times the top and the bottom by root 3 here. And that would give us root 3 over 3. So that's what tan of 30 evaluates to. And that's about it for the common angles, right? 30, 45, and 60 degrees. That's how you can find them. I find it best just to remember the triangles, how you can figure out all the angles and side lengths. And, you know, generally I really just think of these triangles in my head when I'm figuring these kind of questions out. So, question 5. Work out 8.5 divided by 2 2/3. So before you tackle this question, you want to make sure you can quite happily convert between mixed numbers and improper or top-heavy fractions. So let's just take a look at that concept quickly before we have a crack at this. So suppose I had a mixed number, let's say 3 and, let's say, I don't know, 4, let's say 8ths? No, let's say 9ths perhaps. Yeah, 3 and 4 ninths. Okay. Right, so this is a mixed number. It literally means just a whole number of 3 in addition with 4 ninths on top of it. So if you were to draw this as a pictogram, it'd be 3 holes, right? 1, 2, and then 3. And then it'd be 4 ninths after that, which is going to be kind of difficult to draw, but I'll do my best. So there's some fractional part. So yeah, you have to imagine there being kind of 1, 2, 3, 4 ninths to that piece, whereas to each of these holes there'd be how many? 1, 2, 3, 4, 5, 6, 7, and then 8, 9. So to each hole there is 9 ninths. Right, so that's what we're dealing with. 3 and 4 ninths is just 3 plus 4 ninths, which you can see as a pictogram here. So, to convert this to a top-heavy fraction, you're essentially saying how many ninths there are to 3 and 4 ninths. And, when you draw this as a pictogram, it becomes kind of obvious, right? To each hole, there is 9 ninths. And there's 3 holes here. So how many ninths are there in 3 holes? Well, there must be 3 times 9. That's 27 ninths, right? Each hole has 9 ninths, and there's 3 of them, so that's 27 ninths. In addition with the fractional part, which is 4 ninths. And that leaves us with 31 ninths, right? So that's the top heavy, or in proper fraction, equivalent to 3 and 4 ninths. Now, there is a quick way of doing it without drawing all the pictograms out, but I think this way is probably the best way of first learning it. It gives you a really good intuition as to where things are coming from. But, if you want to do this quickly, say if you have some larger numbers, here's generally what you do. You take the 9 here, and then you times it with the 3, and that gives you the 27 here, right? So that's how many ninths there are to 3 holes, and then you add on the 4. So you do the 3 times the 9, and then add the 4, and that's how many ninths you have, and then you just divide that by 9. And that's generally how most people will remember this. So that's going from a mixed number to a top heavy, or in proper fraction. Obviously we can go the other way as well. Let's start with an improper this time. So if let's make one up here. So 20, actually that'd be a bit big. Let's say 13 thirds maybe. That's an improper fraction, and you want to convert that to a mixed number. So yeah, again, you can think about this as a pictogram, right? There's 13 thirds, so to each hole there is 3 thirds, right? 1, 2, 3 thirds. 1, 2, 3 thirds. 1, 2, 3 thirds. How many we got? We got 9 so far. We got another 3 coming on, so that'd be 12 thirds. And then we have one more third on the end, and you can clearly see that's going to be 4 and 1 third. So how can we do that by drawing all these funny little pictograms? Well, you can divide the 3 into the 13, and that's going to give you 4, right? 13. Here's how you might do it in primary school. So 13 divided 3 is 4. And then there's some kind of remainder. There's a remainder of 1. And that remainder is essentially how many thirds you have on the end, right? So we have 4 and 1 third. So 13 divided 3 is 4, and then remainder of 1. So this 4, sometimes referred to as the quotient of this division. 13 divided 3 is 4. That's the quotient. And then this 1 is the remainder of that division. And that goes on top of the fractional part, and that's how you can convert from from improper back to mixed number. That's generally a good way of doing it. So in this question we're okay. So in this question we've got 8.5 divided by 2 and 2 thirds. 8.5 divided by 2 and 2 thirds. So before you want to try and attempt this division, you want to convert both of these to improper. So remember the little technique I showed you? You can do the 2 times by the 8. That gives you the 16, and then add on the 1. That gives you the 17. So that'd be 17 halves. And then we're dividing that by 2 and 2 thirds. So again, let's do the same thing. 3 times by 2. That gives you 6. In addition with 2, that gives you 8. So that's 8 thirds. And now here we need to know how to divide by fractions as well as numbers and so on and so forth. So how do we divide by 8 thirds? Well, I'll just tell you the little rule for the moment. I'm not going to go into full details as to why this is, but I'll tell you the rule. So if you're dividing by a fraction, let's suppose you're dividing by a on b, then it's exactly the same as multiplying by b over a. These two fractions are often referred to as the reciprocal of each other. So a over b, this fraction right here, is the reciprocal of b over a, that fraction right there. And we call them reciprocals because, well, the product of them is always 1, right? If you take a over b and you times it by b over a, then that just gives you 1, right? So we say they're in a reciprocal relationship. It's very similar just of ordering numbers as well. If you took like the number a, it doesn't matter what it is, if you multiply it by 1 over a, you're always going to get 1. So these a and 1 over a are also in a reciprocal relationship. And that's why, whenever you're dividing by a, then it's exactly the same as multiplying by 1 over a. So dividing by something is exactly the same as multiplying by the reciprocal of that thing. So in that sense, division and multiplication are very similar. So here we're dividing by the 8/3, which is equivalent to multiplying by the 3/8, right? 3/8 is the reciprocal of 8/3. So dividing by 8/3 is the same as multiplying by 3/8. And now we just need to know how to remember how to times fractions together. So it's quite a simple rule for doing that. Again, I'm not going to go into exactly why this is. That would be making this question a bit too long, but the rule is quite simple. You just times the numerators together. 17 times with 3, and that would give you, what's that going to be, 51. And then you do the 2 times with the 8, and that would give you the 16. And that's the rule for timesing fractions. You just times the numerators, and you times the denominators. And now we can turn this back into a mixed number, right? So remember the rule to go from improper to back to mixed number. You say how many 16s go into 51. So that's going to go 3 times, right? Because 16 times 3 is 48. And then we get a remainder of 3. And that remainder goes on top of the fractional part, 51. And that right there is our final answer. 3 and 3 51ths. Question 6. A ship is sailing in a straight line from its home port. The distance time graph shows 4 hours of the journey. So on the up axis we have distance here from the home port in miles, and on the long axis we have the time in hours. And the question is, work out the speed of the ship during these 4 hours. So a really critical thing to recognize here is we have the distance away from the home port on the up axis. So this is not the distance accumulated from time 0. This is actually the distance we're away from some port in this case. So that means we're starting right here. What is that? That's 48 miles away from the port. That 48. So here we've got 5 squares, and there's 20 miles to 5 squares. So each square is going to be representative of 4 miles. So 4 miles up, 4 miles up. That leaves you at 48 miles. So this is how far away we are away from the port to begin with. And after 4 hours, well, we've moved further away from the port. And where's that going to leave us? It's going to leave us at 116 miles, right? You do 120 minus 4 is 116, so 116 miles away from the port after 4 hours. So what's the distance we've accumulated? How far have we moved? Right, that's going to be kind of represented by this line here. What's that going to be? 116 minus 48. What is that? 52, 16, 68. 50, 52, 62, 60, 68. Yeah, 68, right? Let me know if I'm wrong. I might be wrong. So 68 miles, and then that took us 4 hours to do that. So how do you calculate speed? Well, you take the distance we covered, and then you divide it by the total time, and that generally gives you the average speed. But in this case, the distance time graph has a constant gradient, so the average speed will just be the speed, right? So speed is the 68 miles divided by the 4 hours, and what is that? There's going to be 17, right? 17 mph, miles per hour. So because we're miles divided by hours, we're going to get miles per hour, and our average speed is going to be 17 miles per hour. It's worth pointing out that this is actually representative of what's otherwise known as the gradient of this graph. So, to calculate the gradient between of a straight line, you take 2 points on the line, and then you do the change in the up, so that's the plus 68 miles here, divided by the change in the along, that's the plus 4 hours in this context. And that's generally how you calculate the gradient of a straight line. So here, the gradient is representative of the speed. Right? Whenever you have a distance time graph, the gradient's always going to be the speed, because the gradient always gives you the rate of change of whatever the up axis represents with respect to whatever the along axis represents. And the rate of change of distance with respect to time is just what we call speed. So that's a good thing to recognize here. The gradient is the speed. Question 7. The sum of the angles in any quadrilateral is 360 degrees. Certainly true. For example, in a rectangle, we have 4 angles of 90 degrees, and that gives us 360 degrees inside, right? Rectangle, right angle, right angle, right angle, gives you 360 degrees inside the quadrilateral. However, Zach writes, therefore, it must be the case that 5 times 90 equals 450 is the sum of the angles inside any pentagon. So he's recognized 4 is like the number of sides here in this equation. And now he's trying to infer that therefore that 4 will now be 5 in this equation, and 5 times 90 will give us 450. So, that's a conjecture, and you can certainly see the thinking behind that, but it's actually an incorrect conjecture. We simply don't have enough numbers to play around with, and the pattern doesn't actually follow that form. Is he correct? No, he's not, and you can quite clearly see why. It's completely impossible for any pentagon to have 5 right angle triangles in it, right? You kind of end up going around twice. You have like 1 right angle triangle, 2 right angle triangle, 3 right angle triangle, 4 right angle triangle, and 5 right angle triangle. It just doesn't make any sense. It wouldn't give you a pentagon. So that's a bit silly. What is the proper reasoning here? Well, any triangle has the interior angle equal to 180. So all these angles inside a triangle, otherwise known as the interior angles, always add to 180. So when you have a quadrilateral, here's a really good argument. You can always cut a quadrilateral into 2 triangles, right? And in this triangle, if you took that angle plus that angle plus that angle, you'd always get 180. And let's use a green here maybe. So that angle plus that angle plus that angle, that'd also be 180 right there. So what do all the angles add up for the quadrilateral? It's going to be all of that one right there, all of that one right there, all of that one right there, and all of that one right there. When you add all those up, you're going to get 180 plus 180. It's just the sum of the angles inside the triangle, which would be the 360, right? So in a quadrilateral, you always get 360 because of that fact. What about a pentagon? Well, you can extend that argument quite happily. Here's the pentagon. 1, 2, 3, 4, 5. And, you can chop this into, well, how many triangles? It's going to be 3 triangles this time, isn't it? So 1, 2, 3 triangles. And inside each of these triangles is going to be, well, again, 180, 180, 180, right? So that angle there, plus that angle there, plus that angle there, that'd be 180. That angle there, that angle there, that angle there, that'd be the 180 as well. And also this angle here, this angle here, this angle here, that'd be the 180 as well. So what's the sum of all the angles inside the pentagon? Well, it's going to be all of those angles, plus all of that angle, all of that angle, all of that angle, and finally all of that angle, so which is just going to be the 180, 180, 180, right? 180, 180, 180 is going to give us 540. So 540 is the interior angle of any pentagon. And this argument naturally extends to polygons of higher number of sides. So if you have a hexagon, it's going to be 4 times 180, which is going to be 720, and then it's 900, and then 1080, and so on and so forth. And yeah, you can actually make a little equation out of that if you like. It's quite a good one to remember. So if n represents the number of sides inside of a polygon, you can always minus 2 from that, and that gives you the number of triangles right there. And then you can subsequently times that by 180, and that's going to give you the interior angle to the polygon, and that's always going to be the case. Whilst we're here, I may as well talk about exterior angle as well, because these two things are very closely tied. Whereas the interior angle is the angle inside a polygon, the exterior angle is kind of the angle you turn through when you hit a vertex. So here we had the interior angle, that one there, whereas the exterior angle, let me do it in red, is actually this angle right there. This would be the exterior angle right there, and this would be the exterior angle right there, and this would be the exterior angle right there. So clearly these are related to the interior angles because they are just the angles on a straight line, right? So the exterior right here and the interior right here, they're always going to sum to 180. So if I called that one little a and I called this one, I don't know, let's call it big A, and that, then it's always going to be the case that A in addition with big A is going to be 180. But there's also a relationship for the sum of all the exterior angles. If here's the exterior angle B, here's the exterior angle C, and here's the exterior angle D, and you can kind of imagine like your little ant, and you're right here, right, your little ant with legs and whatever, and you're kind of walking in this direction. When you hit this vertex, you're going to have to turn through the angle of big A, right? Because you're going to be swinging through the left, you're going to be facing this direction, and then you're going to be facing this direction, right? So you're going to have to turn through the angle of big A. And likewise, you're going to do the same at this vertex here, vertex B. You're going to turn through the angle of big B, and then you're going to turn through the angle of big C, and then you're going to turn through the angle of big D. And by the time you get back to where you started, which is right here, you're going to be facing in the same direction. So what does that tell us? It tells us that the sum of the exterior angles is always going to be 360, because you've essentially span around by one whole circle, right? And you're facing the same direction again. So 360 is always the sum of the exterior angles. And it doesn't matter how many sides you have to the polygon. That's always going to be true. The sum of the exterior is always 360. Whereas the sum of the interior, that certainly does depend on the number of sides. That was the n-2, the number of triangles, times by the 180. That gives you the sum of the interior angles. Question 8. Kim works at an airport in the UK. She records the number of planes landing between 10 a.m. and 2 p.m. each day. The table shows the data for the first 10 days in January. So if you just look at the numbers here, we have, 148, 151, 147, 155, 153, and so on and so forth. So the numbers tend to be hovering around 150 for, here, the number of planes landing between 10 a.m. and 2 p.m. Each day. So the airport was affected by fog on one of these days. Which day do you think it was? And give a reason for your answer. Well, if you look at day 8, we've only got 102 planes landing, which is a significant deviation from, what was otherwise hovering around 150. So I would say day 8 here. And I would say, 102, I guess you could describe it as an outlier. It's not following the general trend of the numbers, right? The general trend of the numbers is to hover around 150. Whereas here it's significantly less. It's about 50 less than what it'd otherwise be. So therefore we might consider an outlier. So part B, Kim uses the data to predict how many planes will land at the airport in a year. In her method, she uses an estimate of 150 planes in each 4-hour period throughout the day. And she assumes the same number of planes each day. So she's assuming 150 planes for every 4 hours, and she's assuming the same number of planes per day. So let's just focus on the day interval at the moment. So here's maybe a line representing 1 day. And how many 4-hour intervals are there to 1 day? Well, you can chop it in the middle. That's 12 hours, and you've got 4 hours there, 4 hours there. There's going to be 3 lots of 4 hours, and 1, 2, 3, that's 3 lots of 4 hours. So you've got 6 lots of 4 hours. to any one day, and within each of those 4 hours, we're getting 150 planes, and so on and so forth, right? So how many planes within a day? That's going to be the 150 times by 6 this time, and that's going to give us 900 planes per day. And then how many days are there to a year? Well, there's 365 if you ignore the leap years. So 365 days, you want to times that with, so days, and then you want to times that with the planes per day. So 900 planes per day, right? And this will give us Kim's estimate for the number of planes within any given year. Now, I'm just going to cheat and do it on a calculator here because my mental arithmetic isn't all that great. So we're getting 328,500 planes, per year. So that's a per year, planes per year. And this was, I guess you could write this as days per year if you like, because then you can see how the day unit kind of cancels, right? Days over days just cancels, and you get left with planes per year. So there is a part C to this question, and part C says, in fact, fewer planes land in winter than in summer, and fewer planes land at night than during the day. What does this tell you about Kim's prediction? Well, if you go back to our calculation, it was all kind of resting on the assumption that within every 4-hour interval, we're getting 150 planes. And that estimate was kind of based on, it was based on the numbers coming in between 10 a.m. and 2 p.m. each day. So it's a bit of a silly assumption, right, to assume the number of planes landing is going to be the same at all periods throughout the day. And this is probably one of the busiest periods of the day for any airport. So assuming 150 planes for every 4 hours, you get a massive 328,500 planes per year. But obviously, that's probably a massive overestimate. So our prediction is going to be too high. And I guess you could say, within 4-hour intervals, we're typically going to get less than, 150 planes for every 4 hours. There's going to be peak periods of the day and lower periods of the day, and the lower periods would be, midnight and so on and so forth, winter. Question 9. The square root of 6 squared plus 8 squared is equal to the cube root of 125 times a cubed. Work out the value of a. So I guess, we can start with the left-hand side here. Left-hand side, that's just the square root of 6 squared plus 8 squared. What is 6 squared? Well, that's 36, one of the square numbers, right? So 36 in addition with 8 squared, which is 64. And then the sum of those two things, well, what's it going to be? 64 plus 36 is 100. We were taking the square root of 100, which is going to give us 10. So the left-hand side just evaluates to 10. Easy enough. What about the right-hand side? Well, the right-hand side, that's equal to the cube root of 125 times with the a cubed. So you need to know a few things about surds here, right? So one of the rules for surds is this, right? The root of a product. So if you have a product like AB, then that's just equal to the product of the roots. And likewise, the root of a fraction is equal to the fraction of the roots. We're not going to need that here, but it's a very similar kind of rule. The root of a over b is the same as root over a over the square root of b. So there's some of your rules for surds. I'm not going to explain where those come from for the moment. I'm just going to get on with the question, I think. So here we have the square root of 125 times by a cubed. And obviously we have a product inside that cube root. We have 125 times by the a cubed. So you can just take the cube root of 125 times with the cube root of a cubed. And you can evaluate each of these cube roots one at a time, right? So the cube root of 125, well, that's just something you probably just want to know, right? You just want to know 125 is one of the cube numbers, and it just so happens to be 5 cubed. And therefore, because 5 cubed is 125, the cube root of 125 is just going to be 5, right? And likewise, the cube root of a cubed, well, cubing and cube rooting are, I guess you could describe them as inverse operations of each other. So the cube root of a cubed is just going to be a, right? So we just end up with 5a, 5 times a on the right-hand side. So therefore, it must be the case that 10 equals 5a. And then it's just a very simple bit of rearranging. You can divide both sides by 5 here. The 5 cancels. 10 over 5 gives you 2. So the a is just equal to 2. And that right there is the final answer. Question 10. Work out the percentage increase from 80 to 280. To work out percentage increase, you need to work out the increase itself. So you're going from 80 to 280. And what's the increase? Well, it's just the difference between these numbers, right? So it's going to be plus 200. So 200, that is, that's the increase itself. And the percentage increase is just the increase itself as a percentage of the original. So here's the original, the 80. And you want to get the 200, that's the increase, as a percentage of the original, which is the 80. So what do you want to do? You want to take that 200 and you want to divide it by the original, which is the 80. And then to convert that to a percentage, you can times it by 100%, which is perfectly fine because 100% is just unit. Oh, well, yeah, it's just 1, isn't it? So this percent sign is representative of 100th. So 100 100ths is just 1, so it's perfectly fine to times by 100% because it's just 1. And then to actually evaluate this, I'm going to do this by hand because it's nice and easy to do. So you can divide the top and the bottom of this fraction by 10. That's going to cancel one of the zeros here. Then you get 20 over 8. So you can divide by 4 there. So 20 divided 4 is going to be 5, and 8 divided 4 is going to be 2. So what are you going to get? 5 halves. 5 halves is 2.5 or 2.5. So 2.5 times 100%, that's going to be 250%. That is your percentage increase. So yeah, put another way, the increase, which is 200, is equivalent to 250% of 80. Right? If you took 250% of 80, you would have 200, and that's being added on to give you 280. So what I like to write the percentages just slightly above these numbers. So 80 is 100% of itself, right? This 200, that's 250% of 80. And this 280, well, that would be 350% of the 80, right? So all these percentages are relative to the 80. And you can see we are actually left with 350% of 80 because we've increased 80 by 250%. And 100% in addition with 250%, that leaves you 350%. So that's the final answer, 250%. Question 11. Here are 4 triangles A, B, C, and D. Which of the 2 triangles are congruent? Circle the 2 letters below. So, I guess you need to know a few things about congruence and similarity to actually approach this. So congruence, if you say 2 shapes are congruent, it essentially means the shapes are, I guess you could say, the same size quite loosely. And that essentially means all the side lengths are the same and all the angles are the same when you're dealing with polygons, at least. So congruence, you have the same sides and you have the same angles. So you might say, hey, all of these triangles are congruent, right? They've all got angles of 56, they've all got angles of 25, and they all have side lengths of 8. But that doesn't mean they're necessarily all congruent because the angles themselves are playing a different relationship to the side length in question. The side length is 8 centimeters, and if you look at the side, the triangle A, we have 8 centimeter length here. That's this length here. And you can see how the angle of 56 and the 25, they are both adjacent to that side length of 8 centimeters. Whereas in the triangle B, say, you can see how it's just the 25 degrees, which is adjacent to the 8 centimeters. And then the 56 degrees is actually opposite. So A and B are not going to be congruent because of that. The relationship of the angles to the side itself is different. What about C? Let's have a look. So you got the 56 is adjacent to the 8 this time. So it's sitting just next to the 8, whereas the 25 is actually opposite the 8 centimeters. So again, we have a different relationship to both the triangles A and B. So B, you have 56 opposite, C, you have 25 opposite, and A, well, they're both adjacent, right? What about D? Yeah, so D is looking good. You've got 25 adjacent, you've got 56 adjacent to this side length of A. So, for that reason, both the triangle A and the triangle D are going to be congruent to each other. So A is congruent to D, and that's the final answer. Question 12. Solve x squared minus x minus 12 equals 0. So what we have on the left-hand side here is a quadratic function in x, and we're solving to 0. This is a pretty typical kind of quadratic problem. How do we go about doing this? Well, there are different ways of doing this. You can straight up use the quadratic formula to solve this. So what is that like? There's like negative b plus minus b squared on 4ac minus 4ac over 2a. It's a bit overkill. I mean, you could use that where the a, what would the a be here? It would be 1, and the b would be -1, and then the c would be -12. Right, but that's a bit overkill. I think this is a non-calculator paper, and it's actually going to be easier to solve this by quadratic factorization. So that's where you write the left-hand side as a product of two linear factors. So one bracket here, one bracket there. They both generally have a single x in, like that, and then equal to 0. And then it's just a matter of figuring out what number goes there and what number goes there. So for the moment, I'm just going to call those numbers a and b, just so you can see how this plays out. If I put a there and I put b there, and let's just have a plus and a plus. And then in the expansion of this of these pair of brackets, each term in the first bracket, and it does end up getting times of each term in the second bracket. So you get this x times with this x, and that would give you the x squared. You get this a times with this b, and that would give you the ab. So that's your constant term. You get this a times by the x, and that gives you the x. And you get this x times by the b, and that gives you the bx, right? So this ab right here, I like to refer to that as the constant term, because it's not dependent on the variable x. So no matter how x changes, this term is always going to be constant on the left-hand side. These two terms here, ax and bx, I guess you could describe them as linear terms, and they have a linear dependence on x. So, and they're both joined together. When you add ax with bx, you're going to get a plus b, lots of x. So these simplify to a plus b, lots of x coming out, and then you just get this x squared term over here as well. So comparing it with the first equation, we had x squared minus x, then minus 12. So this constant term of minus 12, that has to be equal to the AB. So the product AB has to be equal to that minus 12. And then we have minus x. So that's essentially the same as plus, I guess you could say -1 lots of x. So if I just put plus and then -1 in there, squeeze it in, lots of x. And that -1 is how much x we have. And you can see that's equal to the a plus b here. So -1 is equal to a plus b. So the sum is equal to -1. So it now becomes a problem like this. The product of two numbers is equal to the -12. And the sum is equal to the -1. Can you think of two numbers which do that? Well, if the product is negative, then one of those numbers has to be negative, right? Because negative times positive always gives you negative. And moreover, because the sum is negative, the negative number has to be of greater magnitude than the positive number. So what's going to do that? Well, it's going to be -4 and +3. Right? So -4 and +3 are going to be my a and the b. Let's plop those in there and just see how the logic pays out. So -4 x plus 3, and that's equal to the 0. All right, so once you got the product of these two brackets equals 0, well, the logic goes like this. You have a product of two things, and it's equal to 0. And the only way that can possibly be is if one of those products is 0, or maybe the other, or maybe both. So the first bracket, that's going to go to 0 when the x equals 4, because 4 minus 4 would give you 0. So that's actually going to be one of the solutions to this initial quadratic. And then the second bracket, x plus 3, that's going to go to 0 when x equals -3. So you do actually get two solutions to the initial equation. X equals 4, and x equals -3. So, I mean, when you first see this, it may look like kind of magic, but if you don't believe me, you can always plug it back in to what we were initially given and just check that they work. Otherwise known as substituting x in as some value. So let's substitute, let's substitute x as 4 and just see if it works. So you put 4 in the x squared, you're going to get 16. And then minus the x, that'll be -4. And then minus the 12, that obviously gives you 0, right? 16 minus 4 minus 12 is going to give you 0. What about the x equal, what was it, -3? Let's try that one. Well, x squared would be -3 all squared. So that's -3 times -3. Negative times negative gives you a positive. So that's going to be positive 9, the x squared. And then you have minus -x. So you're minusing a negative. When you minus a negative, it's the same as adding the positive. So it's going to be +3 and then subsequently be -12. So 9 plus 3 minus 12, that gives you 0. So you can see both these solutions are giving us 0. And, the logic is working. Question 13. The ratio of E to F is 2 to 3, and the ratio of F to G is 5 to 4. Work out the ratio of E to G. So, I think the best way by far of doing these kind of slightly fiddly ratio questions is to, well, here you can write the ratio of E to F to G just in one line like that. And we can put in the information we'd be given. So what we'd be given that E to F is 2 to 3. Let's put that on that line. And then we're given that F to G is 5 to 4. So let's put that in there like that. So these are two kind of independent ratios. We can actually bring the ratios together, provided we get kind of the same number for F in both the ratios. So at the moment it's 3 here and at the moment it's 5 here. And for that reason, we can't just put a 4 right here because 2 to 3, it'd be like 2 to 3 to 4, and that wouldn't make any sense because F to G should be 5 to 4. So what we need to do is get the number of parts to F the same in both radios. So at the moment we've got 3 parts to F and 2 parts to E in this radio. That's easily dealt with. You can safely times both sides of the ratio by some number, and you maintain the equivalence of the ratio. So if you times 3 by, or let's say 5, and you times the 2 by 5 here, that would give you a ratio of 10 to 15, right? So E to F is 10 to 15. That's the equivalent radio. Let's do a similar thing with the second radio. That's 5 here. You can take that and times it by 3, right, to give us 15. And times the 4 here by 3. That's going to maintain the equivalence of the radio. So it's going to be 15 in the ratio to 12. So, and now we have the same number of parts to the F, right? 15 parts here, 15 parts here. So it's perfectly okay to bring these two ratios together as just 10 to 15 to 12. And now we can see immediately what the ratio of E to G is. It's just going to be this 10 to this 12, right? So E to G, let's do it over here just on its own, 10 to 12. And you can cancel that down. You divide that by 2. It's going to be 5 to 6. And that right there is our final answer to this question. E to G is in ratio 5 to 6. Question 14. A and B are two events. Some probabilities are shown on the Venn diagram. Work out the probability of A. So this A dash means not A. And then this U means union, which essentially means or. And then B. So this means the probability of not A or B. That's what we're being asked for here. So, if you look at the Venn diagram, we have the circle of A, and anything inside A is going to, well, satisfy the event A. That could be any event, right? It could be, some person likes football, or, they like Pokemon or whatever. And then the circle of B, that's, again, just some event. And there's some subset of the entire population. The population here is represented by the epsilon. The population can literally be anything. It could be people, pebbles, whatever. Doesn't matter. Just some population, and some subset of that population is satisfying some event A, and some subset is satisfying some event B. And you can see, the fraction of the population which is satisfying the event B is 0.15 in addition with 0.35. So that would be the probability of B. It's just a half, right? The probability of B is 0.5, right? 50% of the population is satisfying event B. And likewise, at A, right? How many satisfy A? Well, probably that'd be 0.45 because you've got 0.3 in addition with the 0.15. So 45% of the entire population is satisfying the event A, whatever it is. And likewise, you can talk about the intersection. That's the That's represented by the big N symbol, right? So N means intersection, and that means essentially means A and B. So what subset of the population satisfy the event A and B? Well, that's just the 0.15. So 15% of the population satisfy the intersection A and B. So A and B. Now there's one number we're missing on this Venn diagram, and that's kind of the number outside of A and B. Very easy to figure out though, because all the numbers inside the square should total to 1, because probabilities, when you consider all the possible events, or all the possible outcomes I should say, should add to 1. So yeah, what we can do the 1 minus 0.3 minus 0.15 minus 0.35. What is that? That's 0.5 together, and then 0.3 is going to give you minus 0.8. Oops. And that leaves us with 0.2, right? So 0.2 is the remaining probability in this Venn diagram. That's going to go, let me just write that here, 0.2. And that's going to represent the probability that we are neither A nor B. And again, I could write that as an intersection. I'm going to need some dash symbols to do that, right? A dash, and then B dash. That's not A and not B. That's 0.2. Okay. All right. So we're now in a pretty good position to calculate this probability, not A union B. So the union means or, which essentially means you can be not A, you can be B, or you can be both. So we essentially have to include all the space of not A and all the space of B together. There might be some overlaps, there might not. Let's have a look. So all the space of not A, well, that's just anything outside of A, right? So let me try and do that in yellow, right? Anything outside the circle of A is going to be not A. So I'll do my best here. Outside the circle of A, there's all of this yellow space, and that's all represented, well, that's all representing not A. So not A is yellow. What about B? Well, that's just anything, let's make that green perhaps. That would be all of this space here. Anything inside the green circle is going to be the B space. And, what we're going to do is the union of the yellow space with the green space. So that's going to include, that's going to include the 0.15 here, that's going to include the 0.35 here, and that's going to include the 0.2 here as well. So 0.2 in addition with 0.15, in addition with 0.35, and that's going to give us the probability we're looking for. What is that? 0.7, and that's our answer right there. That's the probability of not A union with B, and that's the final answer. Question 15. In a survey, queuing times at supermarket checkouts were recorded. One morning, samples of 50 customers were taken at supermarkets A, B, C, and D. The box plots represents these results. So question 15a, on average, which supermarket had the lowest queuing times? Okay, so to answer these kind of questions, you need to appreciate how box plots work. So this, if you look at the box plot for supermarket A, this right here is the median. The median, I guess you could describe it as the middle value. So if you put all these customers in a line and you arrange them by, how long they had to queue, then the person in the middle would be the median. By similar nature, this guy here is called the lower quartile, LQ. Again, if you put all the customers in a line in order by their queuing times, then the lower quartile would just be the person kind of a quarter of the way in, right? 25% in. That's why this is sometimes called the 25th percentile, because it's 25% into the distribution. And likewise, the upper quartile, very similar kind of thing. This guy is 3/4 of the way into the distribution. So this would be represented by, well, this would be the queuing time of the person 3/4 of the way in to the distribution. So, yeah, I think another good way of looking at this is, if this is 25% into the distribution, and if this is 50% in the distribution, then that means there's going to be, 25% or 1/4 of the people between the lower quartile and the median. So for supermarket A, 1/4 of the people are having to wait between 8 minutes and 10 minutes. And that's how you can read these box plots. And likewise, this is obviously the absolute minimum. So you might call the lower bound minimum, whatever you want to call it. And likewise, this is the, I guess you could describe the maximum or the upper bound. So for part A, they're asking, on average, which supermarket had the lowest queuing times? And to answer that question, you generally want to refer to the median, because the median is one measure of central tendency. So measures of central tendency, they're kind of trying to give you a feel for where, I guess you could say, the center of the distribution is. And you've got different, another way of calculating that is the mean, or maybe you have the median, and there are a few others. I'm not going to mention them here, but the median has the advantage in that it's not affected by outlying values, because it's just finding the middle person and asking them, what's your queuing time? It doesn't matter how many outliers you have on one end. You could have an outlying person waiting, about 30 minutes. It wouldn't really change what the median is, but it would change what the mean is, because the mean accounts for outliers, but the median doesn't. So, for this question, you just want to appeal to the median. Which one is the smallest? Well, it's going to be supermarket C, 4 minutes long, right? So supermarket C, and just make sure you say median equals 4. And just make some reference to the fact that it's also the smallest as well. So 4 minutes, and this is the smallest median. So that's going to be generally the lowest queuing times. I guess another way of looking at that is, again, in terms of proportions, right? If the median is 4 minutes, that means 50% of the population is below 4 minutes. So in this case, supermarket C, we have 50% of the customers waiting between 2 minutes and 4 minutes. And likewise, 50% waiting between 4 minutes and 10 minutes. So that's another way of looking at it. I think that's quite a good way of looking at it. 15b, at which supermarket were the queuing times most consistent? So here we're looking at measures of dispersion. So how spread out is the data? And I guess there's two you can infer from a box plot. You can infer the range, and that's generally just quite simply the maximum minus the minimum. And you can also infer the IQR, the interquartile range, and obviously that's just the upper quartile minus the lower quartile. So which one do you choose? Well, generally you choose the interquartile range, because the range itself, this is highly subject to what the outlying values are, right? So if you look at supermarket A, we got the maximum of 14, but if for some freakish reason a customer had to wait, say, 30 minutes, then the maximum would increase to 30, and the range itself would increase by 16. It would increase to, initially the range was 14 minus 3, that would be 11, but now the range would be 30 minus 3, that would be 27. So there's a massive increase just due to one outlying customer. So the range, it really is highly dependent. Well, it is only dependent on the outlying values, and that doesn't make it a very good measure of dispersion. But the interquartile range, that is for the most part independent, of outlying values. It's just doing the upper quartile minus lower quartile. So it's going to the customer 3/4 of the way and saying, hey, how long did you wait? The customer 1/4 of the way and saying, hey, how long did you wait? And then you're subtracting them, and it's giving you the IQR. So just looking at the box plots, just eyeballing them, you can see the supermarket B is going to have the smallest one here. Right, this is the upper quartile of 7, this guy, and this is the lower quartile of 5. And when you subtract those two, you are going to get the IQR, the interquartile range for supermarket B, and that's just going to be 2. So that's your IQR. This was supermarket B. And this is the smallest IQR. It's the smallest measure of dispersion. So, you can say the queuing times at supermarket B are more consistent than what they are at any other supermarket. Question 16. Circle the number that is closest to the value of 29 cubed. So, this is a non-calculator paper. They don't expect you to do this by hand, although you could. So what do they expect you to do? Well, they want you to take 29 and they want you to round it to one significant figure. So let's go ahead and do that. 1 SF, one significant figure. Here, the first significant figure is the 2, and that's in the tens column. So that means, to one significant figure just means rounding this to the nearest 10. And because 9 follows the 2, you're going to round up to the 30 here. So you just want to round the 29 to 30, and then, we want to do 30 cubed as opposed to 29 cubed. So 30 cubed. And here's a pretty good way of thinking about it. 30 is 3 times 10. So we have a product, and then we're cubing it. And because I have a product cubed, you can just cube each of the products. So you can do 3 cubed times by the 10 cubed. 3 cubed is 27 times by 10 cubed, which is 1,000. And then that just leaves us with 27,000, right? So 27,000 is the approximate answer here. And that's question 16. Question 17. Work out the exact value of 3/4 to the power of -3. So I guess one of the things you learn when you're learning indices is how to interpret negative powers. So let's just take a look at that. Yeah, so whenever you take x and you take it to a negative power, let's say -n, here's the rule. I'm not going to go into why this is at the moment. I'm just going to tell you. So x to the -n. How do you interpret that? Well, when it's a negative power, you can take the reciprocal. The reciprocal of x is just 1 over x. And then you subsequently take that to the positive power, so n. And that's a pretty good way of interpreting negative powers. So if you have a negative power, you do the reciprocal, and then you take it to a positive power. Here we have 1 over x to the n. So when you have a fraction to a power, you just take the numerator to the power and the denominator to the power. So this would be 1 to the n, which is n, and the x to the n, that would just be n as well. And this kind of extends. If you want to take a fraction, if you have a fraction to a negative power, it's the same kind of deal, right? If you have x over y to -n, what do? You take x over y, you take the reciprocal, that flips upside down, so y over x, and then you make that a positive power, right? So y over x to the power of positive n, and then, again, numerator to the n and denominator to the n. So you do y to the n divided by x to the n, and that's how you can interpret a fraction to a negative power. So again, that idea of reciprocal is playing quite a useful role here. The y over x and the x over y, these are reciprocals of each other. And when you have a negative power, you just make it a positive power, provided you make the reciprocal. Likewise, the x here and the 1 over x are reciprocals of each other. You have a negative power, you take the reciprocal and you do it to a positive power. So let's do that here. We have 3 over 4 to the power of -3. So what do? We take the reciprocal of 3/4. 3/4 is 4/3, right? You just flip upside down and then you make the power positive, right? 4/3 all cubed. What is that? Well, you just cube the numerator and cube the denominator now. So 4 cubed divided by 3 cubed. 4 cubed is the 64 and 3 cubed is the 27. And that's about it for this question. You can leave the answer just like that if you want, or you could go to a mixed number here if you really wanted. But that'll be fine. Improper, they haven't asked for a mixed number here. So 64 over 27 is the final answer. Question 18. Beth and Mia translate documents from Spanish into English. A set of documents that would take Beth 8 days would take Mia 10 days. So it takes 8 days for Beth to finish and 10 days for Mia to finish if they're working independently. Beth starts to translate the documents. After 2 days, both Beth and Mia start to work on translating docs. So Mia is joining after 2 days. And the question is, how many more days, more being quite important here, more days will it take to complete the work, and you must show you're working. So I think the best way to reason about this is in terms of fractions of the documents translated. If they tell you it takes Beth 8 days to finish all the documents, then you can quite happily say that Beth completes 1/8 of the documents per day, right? 1/8 of the documents per day. That's how much Beth completes per day. So that's Beth's output in terms of a fraction of the total documents. And by similar nature, Mia, you can say, completes 1/10 of the documents per day. So that's Mia's output if she's working kind of independently. And what they're saying here is, Beth, she's been working for 2 days. So what fraction would she complete in those 2 days? Well, she's going to complete 2 days times by 1/8 per day. So that's going to be 1/4. So Beth will have completed 1/4 of the documents after 2 days. And then the question is, how many more days will it take to complete the work? Well, if we complete 1/4 of the documents, then there must be a remaining 3/4 of the document. All right, so there's 3/4 left to do. And we now need to calculate the rate of output per day if both Beth and Mia are kind of working together. So let's go ahead and do that. Right? If these guys are working together on them, well, Beth's completing 1/8 of the docs per day, and Mia's completing 1/10 of them per day. So together they're going to complete 1/8 in addition with 1/10 of the documents per day. So a bit of fraction arithmetic here. Let's take those and add those up. What's that going to be? I guess we could times by 4, 5 there, that'd be 40. And that'd be 5 40ths. And then times by 4 here, that'd be 4 40ths. And altogether that gives us 9 40ths. So Beth and Mia together, they're completing 9 40ths of the documents per day. And we have 3/4 left over, right? So now it's a simple fraction division question, right? We're going to take the 3/4 which we have left. That's the fraction of the documents left to do. And you want to divide that by the fraction of the documents we can complete per day. So that's going to be 9 40ths, right? So let me just make that a bit clearer. So 3/4, that was how much was left. That's the fraction of the documents left. And this right here is how much of the documents we can complete per day. So that's the fraction of the documents we can complete per day. And that division will give us the answer, right? So 3/4 divide 9 40ths. So remember the rule, dividing 9 40ths is the same as timesing by 14/9. And the 4 here, you can kind of preemptively cancel down because you got a factor of 4 in the denominator here. So that's going to cancel a factor of 4 in the 40 there. That would leave you with 10. And likewise, the 3 here is going to cancel with the 9 on the bottom. That would leave you with 3. So what does that tell us? It's going to tell us it takes us 10 thirds of a day to finish. Right? And maybe that's a bit more sense with a mixed number. So 3 into 10 go 3 times. Remainder 1. So that's 3 3/3 of a day. And that's how many more days it's going to take to complete the remaining work. And that's the final answer. Question 19. In a chess club, there are X boys and Y girls. If 5 more boys and 8 more girls join, there would be half as many boys as girls. Show that Y equals 2x plus 2. So, we're starting off with X boys here, and then we're starting off with Y girls. And 5 more boys join, so how many boys are we going to have? X plus 5 boys, right? And 8 more girls join, how many are we going to have? We're going to Y plus 8 girls. And what they're saying is there'll be half as many boys as there are girls. Or put another way, so the boys here, that's X plus 5, that would be 1/2 of the girls, right? So 1/2 of the girls are Y plus 8, and 1/2 of the girls is equal to the boys. And now it's just a matter of rearranging this equation. So to do that, I'm going to start by timesing this whole side by 2. So I'm timesing all of the X plus 5 by 2. I'm going to times this side by 2 as well, because that would just cancel with the half right there. So you get 2 times of X plus 5. So it gives you 2X plus 10, because you have to times each term by 2 there. And over here, you just get left with the Y plus 8. And then to finish off rearranging that, you just minus the 8 from both sides. So minus 8 cancels. 10 minus 8 is 2, so you get 2x plus 2, and that equals to the y. So that establishes part A. And then part B, again, it's kind of obtuse. So if instead 10 more boys and 1 more girl join, there would be the same number of boys and girls. Work out X and Y. So let's go through the same process this time. We're starting off with X and Y. And then 10 more boys join, so we now have X plus 10 boys. And then 1 more girl joins, so we now have Y plus 1 girls. And yeah, these, what the question is saying is these are now going to be equal, right? They'll be the same number of boys as there are girls. So we can set equality between the number of boys and the number of girls. And then we can rearrange this for the Y. So if you minus 1 from here, minus 1 from here, it's going to cancel the 1 there. And you get X plus 9, and that equals to the Y. So Y equals X plus 9. And the question was actually saying work out what the value of X and Y is, right? So now we have 2 equations. One of them is y equals 2x plus 2. And one of them is y equals x plus 9. So what we essentially have is simultaneous equations, two equations and two variables. And more often than not, you can solve for a unique value in both x and y when you have the simultaneous equations like this. So in this case, I don't need to add or minus the sides at all. We have y the subject, so you can just say, hey, if y equals x plus 9 and y equals 2x plus 2, then it must be the case that x plus 9 is equal to 2x plus 2, because they're both equal to y at the same time, right? So x plus 9 has to be equal to 2x plus 2. And, we can now rearrange this. So you can minus x here, you can minus x here. It's going to cancel one of the x's there. And over here, just get rid of x. And let's just minus the 2 as well. So minus 2 there, minus 2 there. That's going to cancel the 2 there. And that's going to leave us with 9 minus 2 is 7. So the x would be equal to 7, right? That's one solution for the x. And to find the y, well, you can just substitute it into any one of these equations right here. So x equals 7. That's going to be x is 7 plus 9. That would be 16. So y should be 16 from the solution. So x should be 7 and y should be 16. And again, you can always substitute these back into the original equations you formed just to check that they work, right? So is this y equals 2x plus 2 working? Well, let's go ahead and try it out. If you plugged in, say, 7 for the x here, you would get, 2 times 7 is 14, and then plus 2, that would give you the 16 right here. So that's all looking good. And likewise down here, the y equals x plus 9. If you plug in the 7 there, you're going to get 7 plus 9. That would give you the 16 for the y. So that's all looking good as well. So there must be 7 boys to begin with and 16 girls to begin with. And that's the final answer. Question 20. PQ, R, and S are points on a circle. PXR and QXS are straight lines. And we've been given that PX is equal to SX. So you can see that indicated with the little notches here. That indicates same length edges. And here they want you to prove that QS is not a diameter of the circle. So this is a typical kind of circle theorem question in GCSE, right? If you put a diameter across on a circle, and then if you take any point and then you form a triangle with that diameter, then one of these circle theorems says this is always going to be a right angle triangle, provided one side is their diameter. And that kind of works. That kind of works both ways as well. So if you have a cyclic triangle where the diameter is one of the sides, you're always going to get a right angle triangle, and vice versa. If you have a cyclic triangle with a right angle, then it's always going to be one of the sides is always going to be the diameter. There's no other way of getting a right angle triangle with a cyclic triangle. The other theorem you need for this question, because I've kind of thought about it before ahead of time. So the other theorem says if you have, say, 2 points and you go to one other point on the circle, then you get some kind of angle between them. And that angle is kind of independent of the point you go to, right? So this point here, it doesn't matter where you go to with that point. If you go to, say, that point there, you always get the same angle. You can kind of see that roughly from my sketch here. Or if you go over here, say, again, it's going to be the same angle. I've sometimes called this the pointy hat theorem. You probably won't hear it in the textbooks, but that's what I like to call it. So there it is, the pointy hat theorem. And we're going to need that here as well. So how can we apply the pointy hat theorem to this question? Well, if you look at the points Q and R, those are points with lines being taken to other points. So we're taking the Q to P and we're taking R to P, and we're going to get some kind of angle there. And that angle there would have to be the same as, if you took Q to S and R to S, well, it's telling us it's 27 right here. So this angle right here, that would have to be 27 degrees by the pointy hat theorem. Okay, so all that remains for this question is to find this little guy here, and then just show that this is not a right angle triangle. So how can we get the blue angle? Well, the triangle PXS is isosceles, right? Because you have two sides the same length. You have this side and this side the same length. So you have a line of symmetry down there for the triangle PXS. So this angle right here and this angle right here are necessarily going to be the same. What are they going to be? Well, you do the 180 You minus the 50, and that leaves you with the 130. And that 130 is shared equally between the XPS triangle and the XSP triangle. So 130 divided 2, that's going to be 65. Whoops, 65 right there. And 65 right here. So what does that leave us with the angle QPS? Well, 27. Let's write it down. So QPS, you put a little hat on that, just say it's an angle. That's going to be the 27 in addition with the 65. And then what does that leave us with? 85, 92, right? So that is not equal to 90 degrees. And because it's not equal, well, that means you don't have a right angle at the QPS. So it's necessarily the case that QS cannot be a diameter of the circle by this circle theorem right here. And that's the end of the question. Question 21. So here are the first 4 terms of a quadratic sequence: 11, 26, 45, 68. And here they want you to work out an expression for the nth term. So I've got my own particular way of laying these kind of ones out, right? So I'll typically like put n somewhere there, and then n is just used to denote the number of the terms. So you have the first term, the second term, the third term, and the fourth term, and so on and so forth. And in this case, I'm going to use the label u subscript n. That represents the nth term itself. So when n is 1, it's the first term, so that's just going to be the 11 here. When n is 2, it's the 26. Second term, and then it's 45, and then it's 68. So you know, when you're dealing with quadratic sequences, there is like a little methodology a lot of people will learn. They don't always see where it comes from, though. I might show you that here today. Yeah, let's do that. So I'll show you where the methodology comes from for quadratic sequences. Okay, so suppose you had like a quadratic nth term. So suppose un was like, well, let's suppose it's n squared, right? So that just gives you the sequence of 1, 4, 9, 16, so on and so forth, right? And quite often when you first start looking at sequences, you typically start with arithmetic sequences, so that's where you just have a constant common difference. But with quadratic sequences, the first difference is not constant, right? So here we have a first difference of 3, we have a first difference of 5, we have a first difference of 7, right? So this is what I sometimes call the first difference. It's just the difference between the terms, and you can see it's not constant here. However, the second difference itself is constant. It actually turns out to be 2 in this case. And you can kind of see why this is if you just play around with the algebra a little bit. So if you say un, we know it's n squared. So let's denote the first difference to be d, and then I'll call this n, and this represents the first difference, so the difference between the first term and the second term, or I should say the nth term and the n plus 1th term, right? So this is un plus 1, and then minus un. So dn represents the first difference itself, which is itself its own sequence, right? It's just the 3, 5, 3, 5, 7 here. But algebraically, what would it be? It'd be the n plus 1th term. That'd be n plus 1, and then squared, and then minus the nth term, which is n squared. This bracket n plus 1 squared, it expands to, what is it, n squared plus 2n plus 1, and then you're minusing the n squared, and then the n squareds kind of cancel here. You're just left with 2n plus 1. So if you're pretty well studied with arithmetic sequences, you'll recognize this. You'll recognize this too as the common difference, right? And then if you plug in 1 as n, you just get the first term. So 2 times 1 plus 1 is going to give you 3, and that gives you this first term here for the first difference. And then it's just going up by 2 each time. So I guess the point I'm trying to make here is the first difference itself is an arithmetic sequence, and that arithmetic sequence has a common difference, which is just 2. And that 2 is, well, it's related to the n squared here. If you had something like un, suppose you had to say 2n squared. Everything's just going to double, right? Or maybe let's put a plus n in there as well. Let's see what we get. So if you plug in n as 1 into this, you get 3. If you plug in n as 2, what do you get? 2 times 4, and then so 8, and then plus 2 is 10, and then let's plug in 3. So 2 times 3 squared is 2 times 9 is 18, and then plus 3 is 21. Let's just do one more. So 2 times 4 squared, that's 32, and then plus 4, that'd be 36, okay? And again, you can look at the differences here, right? So that'd be a difference of 7, that'd be a difference of 11, and that's going to be a difference of 15. So, you know, again, we're getting an arithmetic sequence for the first difference. And, you know, the common difference of that first difference is just 4, right? So you can see, I'm going to call this the second difference now. You can see how the second difference has doubled. And that comes about, you know, as a result of this 2 being in front of the n squared. So you can see how when you double the coefficient of n squared, you also double the second difference. So generally what people learn when, you know, they're doing these quadratic sequence terms, they'll find the second difference, and then they'll divide it by 2, and that gives you the coefficient in front of the n squared. So 4 divided by 2 just gives you 2. That's the coefficient of n squared, and that's how I'm going to approach this question 21. So for this sequence, we have let's go ahead and take the first difference. So it's going to be 15. And then, what do we got? Oh, my arithmetic. I don't like arithmetic. What was it? 45 minus 26? It was 19, something like that. And then 68. I'm guessing it's going to be 23. All right, yeah, that's right. Good. And then you can see how the first difference here is, second difference is 4, and then it's 4 again. So because the second difference is 4, I can now divide that second difference by 2. Right, so it's going to be 2. That's going to give me the coefficient of the n squared. So 2 times by n squared, right? And now I'm going to consider the sequence of 2n squared. So 2 times 1 squared, what is that? That's just 2. 2 times 2 squared, what was that? That's just 8. 2 times 3 squared, what was that? 2 times 9 is 18. And then 2 times 4 squared, that's 2 times 16 is 32. Okay? And now what I'm going to do, you know, I'm kind of looking to find, you know, the other part to this this nth term. So I know I have 2n squared, but you know I might have some n part as well. So there might be some amount of n, and then there might be some constant on the end as well. So I need to figure out what these last two terms come out to be. So what I'm going to do the nth term, and then minus the 2n squared, and I'm going to put that on its own row. So the nth term is un minus 2n squared. Let's go ahead and do it. So 11 minus 2, that gives us 9, right? 26 minus 8 is 18. 45 minus 18. Oh my god, arithmetic time. What is that? So minus 20, 25, add to 27, right? And then 68 minus 32. Yeah, that's going to be the 36 here, right? And you can see these numbers 9, 18, 27, 36, they're kind of forming their own little nth term sequence. And this one's actually arithmetic because the common difference is constant, right? You just have a constant common difference of 9 here. So these numbers 9, 18, 27, 36, they're forming their own arithmetic sequence, and the nth term of that arithmetic sequence is just these terms on the end that I'm trying to find. So, you know, 9, 18, 27, because the first difference is 9, you just take the 9 and then you times it by the n. And then, you know, you normally have to add some constant here to make it work for the first term, but you don't need to do that here, right? Because when n is 1, you just get 9 times 1 is 9. And that's what we have here, right? So 9n is just the nth term of these terms here, 9, 18, 27, 36. So when I add 2n squared to 9n, that's going to give me what I want, right? So the nth term of the initial sequence is 2n squared plus 9n. And there is no constant on the end. And that's what we're looking for here. So let me just get rid of that. Here's my answer, 2n squared plus 9n. And of course, you can kind of go back and check this if you're really not sure that you've done it correctly, right? Just go ahead and chuck n as 1 in here and n as 2. And just see that it works, right? So you chuck it n as 1, you get 2 times 1 squared is 2 plus 9 times 1. That gives you 11, right? So that works. You chuck n as 2 in here, you get 2 times 2 squared is, what was it, 4 times 2 is 8. And then plus 9 times 2 is 18, so 18 plus 8, that gives you 26, right? And obviously you could do it with these ones as well. So pretty confident that we've got that one right. Question 22. Solve x all over x plus 4 in addition with 7 over x minus 2 equal to 1. So let me just write that out. This is one of the subset of the algebraic fraction questions you often get in GCSE papers. So x over x plus 4 plus 7 over x minus 2, and this we're going to set equal to 1. Okay. So, I mean, there are different approaches you can take here. One approach is to try to combine the fractions by making the denominators the same. I actually find that to be quite a bit more legwork than just, it's probably easier just to times it by the denominators themselves straight away on both sides of the equation, because then you get rid of the fractions altogether. So that's what I'm going to do. I'm going to take this whole side, and I'm actually going to times it by x plus 4. And let me just do this one at a time so you can see how it all works. So I'm timesing this whole bracket by x plus 4, and of course I'm timesing the left hand side by x plus 4. I've got to do the same with the right hand side. X plus 4, I'm timesing there as well. Okay, so you have the x plus 4, and it's going to be times with this first fraction here. And when you times it with the first fraction, it's just going to cancel the denominator, which is what I'm looking to do. So that's just going to give us x as the first term. And then when you times it with this second fraction, 7 over x minus 2, well, you just have to introduce the x plus 4 as a factor into the numerator, right? Because you're taking a fraction and you're timesing it by something. So if you have like a over b and you're timesing it by c, then you can just bring that c as a factor into the numerator. So you can just write it as ac over b. So that's essentially what I'm doing. It's just I'm using algebraic factors, right? The algebraic factor here is the x plus 4. So that's going to go inside the numerator as 7, lots of x plus 4. And then that's all divided by x minus 2, and this is going to be equal to 1 times x plus 4, which I can just write as x plus 4. All right. I'm going to do that again, but this time I'm going to do it with the other denominator of x minus 2. So take that left-hand side, times it with x minus 2. Take the right-hand side, times it with x minus 2. And similar things are going to happen, right? The first term here is just going to be x times x minus 2. So that's just going to leave us with x times x minus 2. And what about the other one? So you're timesing x minus 2 with this whole fraction here. It's just going to cancel the denominator, right? So the x minus 2 there is going to get cancelled with the x minus 2. So we're just going to be left with 7, lots of x plus 4. And that's going to be equal to x plus 4. Times with x minus 2. And now we have to expand it all and then shift it to one side and then hopefully be able to solve it just by rearranging. So let's go ahead and do that, right? So x times x is the x squared. X times minus 2 is going to be minus 2x here. 7 times x is 7x. Well, as you go, 7 times 4, it's going to be 28 coming out as well. This is all being added up on the left-hand side. And on the right, it's a double bracket expansion. So you get the x times x is x squared. You get the 4 times negative 2, that's minus 8, right? And you get the 4x coming out as well. And then you also get the minus 2x coming out. And again, these terms are going to come together, right? The minus 4x and the minus 2x, they're going to come together as a single term because they're both multiples of x. So they're sometimes called like terms, right? So 4x minus 2x is just 2x. We have the x squared as well. And that's in addition, that's with the minus 8 as well. And over here, likewise, the minus 2x and the 7x would come together just to give us 5x as well. So I think I'll just do that straight away. The minus 2x at 7x gives us 5x. Okay. So what do we get? We get x squared plus 5x plus 28. Running out of space. X squared plus 5x. What was it? Plus 28. And that was equal to x squared plus 2x minus 8. So now, you can just minus x squared from both sides. So minus x squared here, minus x squared here, and that's just going to cancel the x squared on both sides. You can minus the 2x on both sides. Minus 2x here, minus 2x here, that would cancel the 2x here, and over here you just get 5x minus 2x, it's going to give us 3x. And then, well, I want to get all the constants to the other side, so what I'm going to do, I'm going to minus 28 as well. So minus 28 here, minus 28 here. It's going to cancel the plus 28. So on the right, you get minus 8 minus 28. Where's it going to leave us? It's going to leave us at minus 36. Right? Because you're starting with negative 8, and then you're minusing the 28. Whenever you minus 28, it's going to send you further down the number line, irrespective of what you're minusing it from, right? So don't make this, and that's going to leave us at minus 36. Okay, and then you can take the 3x divided by 3, you can take the 36 and divide it by 3, that's going to cancel the 3 there, and the x we get as a solution, 36 divided by 3, is finally going to be negative 12. So you can see there's a fair few steps to that question. There's a reason it's towards the end, and there's a reason it's worth 4 marks. But that's the end of that question. Question 23. Prisms A and B are similar. The cross sections are shaded. Prism A has a volume of 480, and prism B has a length of 30 centimeters. And they've told us the ratio of the cross section of A to the ratio of the cross section to B is 4 to 9. So that's the ratio by area. Let me just write that down over here. That's going to be really important for this question. So the ratio by area is 4 to 9. And that's the ratio of A to B. The ratio by length, well, because both these shapes are similar, the ratio by area is, well, when you have similar shapes, the length, the area, and the volume ratios are always related. If you have a ratio by length, let's just call it A to B for a second. So that, here you might have some length, let's call it, it might be 20 there, and here it's going to be a length of 30, so that'd be a ratio of 2 to 3 for that length. And it doesn't matter what length you look at, if they're similar shapes, the ratio by corresponding lengths will always be the same. The ratio by area, well, if they're similar shapes, the ratio by area is always going to be A squared in ratio to B squared, whatever A and B are. Doesn't matter what they are. And it doesn't matter what area you look at. You could look at the area of this face, or you could look at the area of this face, or you could look at the entire surface area of the object. It really doesn't matter, just so long as it's some kind of area on the shape. And the ratio by area is always going to be kind of the ratio by length squared, because area, well, what is area? It's always a length times a length, right? So if the ratio by length is A to B, the ratio by area is A squared to B squared. And by the same argument, any kind of volume for similar shapes is going to have a ratio of A cubed to B cubed. So this is how the length, area, and volume ratios tie together for similar shapes, and that's going to allow us to solve this question. So here we have a ratio by area of 4 to 9. So we can figure out what the ratio by length is going to be, right? It's just going to be kind of the square root of these numbers, so 2 to 3. So the ratio by length, and any length on A has 2 parts, and any length on B would correspondingly have 3 parts. So if you look at this length here on the prism B, is 30 centimeters. That represents the 3 parts here. So this length here is going to be the 20 centimeters. That's going to be the 2 parts, right? And we're well on our way to solving this question. What was the actual question? Work out the area of the cross section of B. Okay, so to do that, we're going to need to figure out the area of A first. So we need to figure out this cross-sectional area here. We've got all the numbers to do that now, right? Because you've got the volume, you've got one length. And for a prism, how do you get the area? How do you get the volume? You always do the cross-sectional area times by the length, right? Area times length for a prism gives you the volume. And what we want to get here, if I could spell, is the area. So the area of cross-sectional area A is going to be the volume, which is 480 centimeters cubed, and you want to divide that by the 20 centimeters, and that's going to give you 24 and then centimeters squared, right? So that's going to be this little green area here, 24 centimeters squared. And now to figure out the area of the cross-section of B, well, we just want to use this area ratio again, the one they told us. So the area ratio is 4 to 9. So this 4 parts is representative of this 24 centimeters squared. So this area here, well, it's going to be representative of 9 parts. If 4 parts is 24, then 1 part would be 6. So 9 parts would be 9 times 6, which would be 54, right? So it's going to be 54 centimeters squared. And that concludes this question 23. Question 24. Show that 2 root 6 all over root 5 minus root 3 over root 10 can be written in the form c root d all over 10. So, what do we have? We've got a few surds, we've got a few fractions, and we want to pull these fractions together at some point. So that's going to involve making the denominators the same at some point. But before we get to that, we might want to deal with some of these surds. So what I'm going to do here is rationalize the denominators of both these fractions to begin with, right? So if you times the top and the bottom of this one with root 5 and then root 5 again, the root 5 times by the root 5 here, that would give you, well, just 5 on the bottom, right? And then we have the root 5, and we can take that in product with root 6, and that would actually give us the root of 30. And that's just me using the rule for surds again. So, the root of a product is the product of the roots. You can quite happily go forwards and backwards on this when you're working with surds. So I'm actually going backwards, right? So I'm going from the right-hand side to the left-hand side. Root 5 times root 6 is just the root of 5 times 6, which is the root of 30. And we also have the 2 in here as well. So that's just 2 root 30 all over 5. And we can rationalize the denominator on the second fraction as well. That just involves times in the top and the bottom by root 10 here. So yeah, on the bottom we got the root 10 times by the root 10. That's going to be, what is it going to be? Just 10, right? root 10 is just 10. And then likewise, same kind of deal. Root 3 times by root 10 on the top. That just leaves us with root 30. And we still have the subtraction here. Now, before we try and subtract these, you want to make the denominators the same, right? So let's go ahead and just times this one up by again. Let's do it by 2 this time. So that's going to give us 2 times 5 on the bottom. That's going to give us 10. And you get 2 times 2 on that. It's going to be 4. So you get 4 root 30. And then minus root 30 all over 10. And now, because the denominators are the same, you can just minus the numerators against one another. So you get 4 root 30 minus root 30. That just leaves you with 3 lots of root 30 and then all over 10. All right, and that actually puts it in the form that the question asked for. We have, this 3 here is our c, and this 30 here is going to be, the d, what's under this square root. So that concludes this question. So question 25, a quadratic curve intersects the axes at the coordinates of -3, 0, 3, 0, as well as 0, 18. And from that, they want you to work out the equation of the curve. So there's a bit of knowledge you probably want to have in your head before you try and attempt this. So this is all to do with factorized quadratics and how they behave and so on and so forth, right? So if you have a factorized quadratic in this form, so if you have x minus a times of x minus b, and you say this is y is equal to that, then the quadratic, it's going to be a positive. It's going to be a positive quadratic. And what I mean by that is the x squared term. When you do x times x, you get positive 1 lots of x squared. So because the coefficient of x squared is positive, this is what I call a positive quadratic. And the reason we pay so much attention to the coefficient of x squared is it determines the overall shape of the curve. Because x squared, it always becomes the dominant term as x gets very positive or x gets very negative. So whether the coefficient is positive or negative, that determines whether you have like a smiley face quadratic, right? That's a positive quadratic, or a negative quadratic. Always does this kind of thing. All right, so something to bear in mind. This is positive x squared quadratic, and this is minus x squared quadratic. So this quadratic here, we've actually got x equal a as a root. So we're going to hit the x-axis at a here, and we're going to hit the x-axis at b. And the quadratic is just going to pass through those points. And it's going to be looking a little bit like this, right? Positive quadratic with roots at a and b. And it would be hitting this point here. Where would it hit? Well, that's going to be the constant term coming out here. That's going to be the negative a times negative b. That would just be ab. Because all the other terms are dependent on x. So when x is 0, that's on the y-axis. The y-intercept would be the product of ab. So it's going to intercept the y-axis at ab itself. So with that in mind, let's have a look at the questions. So you can see this is unsmiley face, right? It's a negative quadratic. So we know we're going to have some kind of negative x squared in here somewhere. You got the 3 and you got the negative 3 as the roots. So it must be the case that we have we must have like x minus 3 in there somewhere, because that would give us the root of 3, and we must have x plus 3 in there somewhere as well, because that would give us the root of negative 3. Now at the moment that would give me positive x squared coming out. So what I'm going to do, I'm just going to flip the x and the 3 around here. I'm going to write it, instead of x minus 3, I'm going to write it as 3 minus x, because that would still leave the root of 3 in there, right? When you put x's 3 in here, you still get this factor in the bracket would still go to 0. But now I'm getting the minus x squared coming out, which is going to give me, right, the big old unsmiley face. So this is what we're looking for this question. However, at the moment, the constant term, when you take the product, you get the 3 times by the 3, and that would give you the 9. When in fact we want to get 18 coming out, right? The y-intercept. So how do we do that? Quite simply, you just lob a 2 in front of these brackets, right? So you can see when x equals 0, you're just going to get 2 times by this bracket here would just be 3 minus 0, it's just 3. And this bracket here, when x is 0, is just going to be 3. So that'd be 3 times 9 times 2. That give you the 18 when x is 0. And that's going to be the y-intercept. That's what we want. So the equation of the curve is given by this factorized quadratic here. And if you really wanted, you could go ahead and expand that. I don't think it's fully necessary, but let's just go ahead and do it anyway. So you're going to get 2 lots of what's going to come out here. You're going to get the minus x squared. You're going to get minus 3x plus 3x. Those two terms would cancel, because this is very similar to like the difference of 2 squares. And then you get the 3 times 3, which is going to be plus 9. So you get 2 lots of all of that. And then again, you can do 2 lots of 9, it's going to be 18. And then 2 lots of minus x squared, that could be minus 2x squared, right? So this right here is probably the simplest way of writing the final equation of the curve. So that's equal to y, and that concludes this question. Question 26. The area of this triangle is 25 root 3 centimeters squared. So here we have a length of w, which we don't know, a length of x, which we don't know. We've been given one of the lengths, which is 20, and we've been given one of the angles as well. And they want you to work out the value of w in the form a root b. Given that the area is 25 root 3. So that's where we're going to start with this question. We're going to start with the area. And that's because, well, how do you get the area of any general triangle? Let's just remind ourselves. So if you have a general triangle, here's any general triangle. Let me call this side A, and let me call that side B. And then the angle between them, let's call it capital C, like that. And the area is always the base times the height times the half. So it doesn't matter what side you call the base. Let's just call this side the base in this case. And then the height would be the height perpendicular to that base. So this height here, that's going to be my height. How can you calculate that height? Well, you can use a little bit of trigonometry, right? Here we have a right angle triangle. The height is playing the role of the opposite to the angle C. So it must be the case, therefore, that sine of big C is equal to the height, let's call it h, divided by the hypotenuse, sorry, so the opposite divided by hypotenuse is going to be b, right? So the hypotenuse there is b. So that allows you to find the height, right? The height is going to be the b times by the sine of the capital C, and we can now find the area of any general triangle. This is a formula you probably just want to remember for the GCSE exam. So it's going to be 1/2 times with the base of A times with the side length B, and then times with sine of the angle big C, right? So this guy right here is our height, and that's a half times the base times the height. Gives us the area of any general triangle. So the most important takeaway here is it involves two lengths and the angle in between them. So that's essentially four variables, right? You have an area as a variable, you have one length as a variable, you have another length as a variable, and then you have the angle as a variable. And this is a relationship between those four variables. Now in this question, what do we have? We have the area, right? We have the 20, that's one side length. We have the x, which we don't quite know yet. Don't know. And then we have the angle 60, which we do know, right? So we know three of the variables. We want to find the fourth variable, and we're going to use this equation here to do that. So the area is 25√3, and that's going to be equal to the half times by the side length A, that's just going to be our 20 here, times by the B, which is x, and then times by sine of 60 degrees. Okay, so this is where you need to remember what sine of 60 is. Again, this is a common angle triangle. So you might remember how that triangle looks from the previous question. It looks a bit like this, if you can remember. So you have like a √3 here, and you have like a 2 here, you have like a 1 here, and there's a right angle. And this is like 60 degrees here, and this is 30 degrees here, and that's going to tell us what sine of 60 is. So sine of 60 is the opposite of √3 over the hypotenuse of 2, right? So this is just √3 over 2. This sine of 60. What else do we have? We have the half times 20. We can just cancel that down to 10. Let's just write that out. So you got 10 times by the x times by the √3 over 2. So I guess we could cancel the half with the 10 again. Half of 10 is going to be 5 here. So what do you get left on the right hand side here? You just get 5 times √3 times by the x. Oops. And that's equal to the 25√3. So what do we do now? You can just divide both sides by the √3, right? You take this side, divide it by √3. You take this side, you divide it by √3. That cancels the √3 here, √3 here. You can also divide by the 5 as well. Let's go ahead and do that. Cancels the 5 here, and then 25 over 5. That's just going to leave us with 5. So x, we've figured out the side length x is going to be 5. So that's the first part of this question. Quite a long question. So x is 5. So how can we go about figuring out what w is? Well, we need to use another rule for triangles, right? That's the cosine rule this time. I'm not going to prove that here. I'm just going to state it. So if you have any general triangle, like that, if this is a side length of, well, let's be consistent, right? So if this is a side length of A, this is a side length of B, this is side length little c, and let's call the angle in between these two guys big C. And here's what the cosine rule says. It says this side length, let's call it little c squared, is equal to the other two sides adjacent to the angle squared, so a squared and then b squared, and then take away 2 times the product of those two sides adjacent. So two sides adjacent, that's going to be a and b, and then times by the cosine of the angle in between them, which is going to be the capital C. So that's what the cosine rule tells us. And again, you have to recognize the variables and the relationships here. This is a relationship between three lengths, right? You have the A, the B, and the C. That's three lengths, and you have an angle as well. So if you don't know any one of these things, you can always use the cosine rule to figure out the other one, right? And that's what we're going to do here. So here, the A and the B, that's what I was calling the two sides adjacent. That's going to be the 5 and the 20, right? And then you have the angle of 60 in between them. And we want to figure out this guy here, the W. So for this triangle, what's it going to be? It's going to be the W squared equals the 5 squared plus 20 squared minus the 2 times by the 5 times by the 20 times by cosine of 60 between them. And let's go ahead and evaluate that, right? So 5 squared is 25, 20 squared is 400, 2 times 5 is 10, times 20 is 200, and then cosine of 60, again, we want to look at our common angle. Let's go back to the previous page. Here's 60, cosine is the adjacent over hypotenuse, so that's going to be 1 over 2, that's a half. So cosine 60 is a half there, 1/2. And we're just tidying that up a bit now. So 200 times a half is 100. So this whole thing just goes to 100. 100 plus 400 is 500, and then 525. So W squared is 525. And then to finish this off, you just want to take the square root of both sides. So the W itself is going to be the square root of the 525, which is the same as, well, again, we can break it down using surds. So 525 is the same as 25 times by, what's it going to be, 21, I think? Am I right? 21? Yeah, I think I'm right, 21. So, and then the root 25 here is just 5. So this is going to be 5, and then root 21. And that puts the answer in the form that we were looking for. The A here is the 5, and the 21, that's the B, is 21. So that concludes 26. And question 27. Here is a sketch of y equals cosine of x with the values of x from 0 to 360. Alpha is an acute angle, and cosine of alpha is equal to k. So you can see that on the graph here. When the angle is alpha, the output is k. And the question is, circle the value of cosine of 180 minus alpha. So, you can kind of eyeball this. Just, if you want to do this roughly, you can see how this length here would be the alpha, and then 180 minus alpha. Well, here's 180, and you're going to go, kind of go backwards by alpha roughly, and it'll put you here roughly, and then, so that's roughly 180 minus alpha there. And, if you go down, let me do this in green perhaps. If you go down and then you go across, and you can kind of see just by symmetry that this y value here would be negative k. So negative k, you could say is the answer, and you'd be correct for that one. But if you want a more precise argument, perhaps it's best to look at the unit circle. So let's look at the unit circle. If I could draw straight lines, which I can't at the moment. So, alright, so here's a circle, and I'm going to take it to be a radius of 1. That's why we call it a unit circle, right? So this is a radius of 1. And I'm going to take the angle, as always, take the angle here to be, counterclockwise from the x-axis. So if this is x and this is y, then the angle theta is just the angle counterclockwise from the x-axis. And this coordinate right here, you can actually express in terms of cosine and sine. The x-coordinate of this little green is actually cosine of the angle. And likewise, the y-coordinate is actually sine of the angle. And you can kind of see why that is. If you look at this triangle here, let's just blow it up a bit. The angle is theta right here, and then you have a right angle right here, and this distance here is that's the x coordinate of my green coordinate, and the hypotenuse here is 1. And likewise, this distance here would be kind of the y coordinate. And the x and the y, you can actually get them, just by using trigonometry, right? So sine of theta is, what is it? It's the opposite divided by the hypotenuse. So the opposite is y. The opposite to theta is y. And the hypotenuse is 1. And y divided by 1 is just y. So sine of the angle is just the y value. And likewise, cosine of the angle is just x divided by hypotenuse is just 1. And that gives you x. So again, the cosine of the angle is just the x value. And so this is how the unit circle definition and the triangle definition of the trigonometric functions tie together. When you're dealing purely with the unit circle definition, you just say, hey, let's take the angle to be counterclockwise from the x-axis, and then you can literally define the x-coordinate to be cosine of that angle. That's essentially a redefinition of the cosine function, but it has the added advantage that the angle can be obtuse, it can be greater than 90, right? So if you're over here, say, then the angle would be obtuse, or it could be negative. If instead of going counterclockwise, you go clockwise, and negative angles are perfectly fine in that convention. So the unit circle definition of cosine, sine, as well as tan is much more powerful than the ordinary triangle definition where you just do opposite divide, hypotenuse, and so on and so forth. Oh, and by the way, tan here, that's just the opposite over the adjacent. So in the unit circle definition, that's just defined to be the y value divided by the x value. So with that in mind, you can reason about these things like question 27a here a bit more precisely, I suppose. If you look at the unit circle here, you have the angle theta counterclockwise from the x-axis, and cosine of the theta is just the x-coordinate of this guy here. But what about if you did the angle of 180 minus theta? Well, that would kind of be this angle right here. That'd be 180 minus the theta. That's the angle counterclockwise from the x-axis, and that would leave us with the remaining theta right there. So this coordinate, well, the x-coordinate of that coordinate, what's it going to be? You can see just by symmetry here, it's actually going to be the negative of whatever the x-coordinate of this coordinate over here is. So the x value gets negated when you go from theta to 180 minus theta, and for that reason, the output of the cosine function actually gets negated as well. So here, the cosine alpha is k, but when you do 180 minus alpha, it negates the output because the x-coordinate, the x components of these coordinates gets negated when you go from theta to 180 minus theta as the angle. Whilst we're here, you could also reason about what the sine function does, right? The y value of this coordinate here is just sine of the angle, and you can see when you go from the angle theta here to the angle of 180 minus theta, the y value doesn't change. So what does that mean? It means the output of sine doesn't change when you go from theta to sine of 180 minus theta. So, in the same token, you could say sine of let's call it alpha is the same as sine of 180 minus alpha. And yeah, you get all sorts of symmetries like that just cropping up from this unit circle definition. I encourage you to have a play around if you have the time. And then 27b, circle the value of cosine of 360 plus alpha. Again, this is just periodicity on the cosine, right? So here's the alpha as the angle, and if you go forwards by 360, this whole graph just repeats. So it comes down here and goes again, and then 360. So if this is alpha, then this over here would be the 360 plus alpha. That one there, right? And you can see it's just going to give us the same output for the y value there. So this right here is the 360 plus alpha on the angle axis, and the y value is the same just by virtue of periodicity. The cosine function repeats itself every 360. That's the repeating unit, And therefore cosine of 360 plus alpha is just the same as cosine of alpha, and cosine of alpha here was equal to k. So the solution to this this question is just going to be k. And that concludes question 27.